In the previous chapter, we learned that the spontaneity of a chemical reaction can be predicted from its free energy change. If the free energy of the products is lower than the free energy of the reactants, that is, delta G is less than 0, then the reaction is spontaneous. If delta G is greater than 0, the reaction is non-spontaneous and the reverse reaction is spontaneous. And if delta G is equal to 0, the reaction is at equilibrium. We also learned that the term spontaneous doesn't mean that the reaction proceeds at a very fast rate. In fact, the term spontaneity has nothing to do with the speed of the reaction. For example, let us consider the following reaction. Aqueous sodium chloride reacts with aqueous silver nitrate to form aqueous sodium nitrate and AgCl precipitate. This is an example of precipitation reaction. And the second reaction we have is carbon in the form of diamond changing to carbon graphite. For both these reactions, the delta G is less than 0. That is, they are both spontaneous. Reaction 1 is an instantaneous reaction. That is, the precipitate is formed as soon as you add a solution of silver chloride to silver nitrate. On the other hand, the conversion of diamond to graphite is so slow that it is undetectable to a human eye. Therefore, the phrase diamonds are forever. Now, how fast the reaction proceeds does not depend on the initial and final state of the reaction, but it depends on the path of the reaction. That is, how the reactants are converted into the products. So, this is the difference between thermodynamics and kinetics. Thermodynamics talks about the initial and final state of the reaction, and consequently, if the reaction is spontaneous or not. On the other hand, chemical kinetics talks about the path of the reaction, and consequently, how fast the reaction proceeds. Let us now define what chemical kinetics is. Chemical kinetics is the study of reaction rates, that is, how fast reactions proceed, and their mechanisms, that is, the detailed events involved in the reaction. Before we define the term reaction rate, let us recall how we define the average speed of a car. Let us say we are driving a car and at time t is equals to 0, the car is at 0 meters point. After 1 second, it traveled up to 6 meters point. After 2 seconds, it is at 11 meters. And after 3 seconds, it is at 15 meters. The average speed of the car in the first 1 second interval can be calculated by the formula. The average speed is equal to the distance traveled by the car at 1 second minus distance traveled at 0 second divided by the time interval difference, that is 1 second minus 0 second. If we plug in the values, we get 6 meters minus 0 meters divided by 1 second minus 0 second. So, the average speed of the car in the first 1 second interval is 6 meters per second. We can do the same thing for the second time interval, that is from 1 second to 2 seconds. The average speed is equal to the distance traveled at 2 seconds, which is 11 meters, minus distance traveled at 1 second, which is 6 meters, divided by 2 minus 1 seconds. If we do the math, we get 5 meters per second. And we can continue to do this for the third 1 second interval, and we get 4 meters per second. Or we can calculate the average speed of the car over the entire 3 second interval. That is, average speed is equal to the distance traveled at 3 seconds, that is 15 meters, minus distance traveled at 0 seconds, that is 0 meter, divided by 3 seconds minus 0 seconds. If we do the math, we get 5 meter per second. So the formula that we are using to calculate the average speed is distance final minus distance initial divided by time final minus time initial. Let us now apply this concept for a chemical reaction. Let us say we have a hypothetical chemical reaction. Reactant A gives product B. And at the beginning of the reaction, that is at time t is equals to 0 minutes, only reactants are present in the container. Over time, the reactant concentration keeps decreasing and the product concentration keeps increasing. We can express the average reaction rate, that is how fast the reaction proceeds, in the same way we expressed the average velocity of the car. Since we have the reactant concentration going down and product concentration going up over time, we can express the reaction rate both in terms of products and reactants. That is, how fast the products are forming or how fast the reactants are being consumed. First, let us express it in terms of products. The average reaction rate is equal to the concentration of the product at time t2 minus the concentration of the product at time t1 divided by t2 minus t1. And we represent the average reaction rate by writing delta concentration B by delta T. The square brackets means the concentration in molarity, and the triangle or delta represents the change in that concentration. Therefore, the units for the reaction rate are molar per second or moles per liter per second. For example, the average rate of appearance of B in the first 2-minute interval is the concentration of B at 2 minutes. We have 4 molecules of B. Let's assume this as concentration minus the concentration of B at time 0 minutes, that is 0 molar, divided by 2 minutes minus 0 minutes. This is the rate at which the products B appear in the reaction. Let us now express the average reaction rate in terms of the rate at which the reactants A disappear in the reaction. The average reaction rate with respect to A, that is delta concentration A divided by delta T is equals to the concentration of A at time t2 minus the concentration of A at time t1 divided by t2 minus t1. In the earlier slides, we learned that the concentration of the reactants decreases over time. So, the concentration of A at time 2 is always lower than the concentration of A at time t1 if t2 is greater than t1. Which means the numerator of this equation, that is concentration of A at time t2 minus the concentration of A at time t1, is always less than 0. That is, it has a negative sign. In chemical kinetics, it is customary to show the reaction rates as positive numbers. Therefore, we multiply both sides of this equation with -1. The negative sign in front of the reaction rate tells us that A is the reactant in the reaction and that its concentration is decreasing over time. If we plot the concentration of reactants and products on the y-axis and time on the x-axis, we get the following graph. As we can see, the concentration of A, that is reactants, in blue line keeps decreasing with time, and the concentration of B, products, increase with time. The average reaction rate over a given period of time is nothing but the slope of line joining 2 points along the curve. Let us now calculate the average reaction rate of a chemical reaction. Nitrogen dioxide decomposes to form nitric oxide and oxygen gas according to the following equation. We start the reaction and measure the concentration of nitrogen dioxide, nitric oxide, and oxygen at various time points in 50-second intervals. Here is the data collected. We have concentration of reactants and products at various time points during the reaction. Now the question is, calculate the rate of disappearance of NO2 for the first 50-second time interval. Pause the video here and try to answer this question. For the first 50-second time interval, the initial time is 0 seconds and the final time is 50 seconds. And the concentration of NO2 at 0 seconds is 0.01 molar and it decreased to 0.0079 molar at 50 seconds. According to the formula, the rate of disappearance of NO2, that is delta concentration NO2 divided by delta T, is equal to the concentration of NO2 at 50 seconds, which is 0.0079 molar, minus the concentration of NO2 at 0 seconds, which is 0.01 molar, divided by T2 minus T1, that is 50 minus 0 seconds. If we do the math, we get negative 0.000042 moles per liter second. As we discussed earlier, it is customary to show the reaction rates as positive numbers. Therefore, we multiply both sides of the equation with -1. We get negative delta concentration NO2 by delta T is equals to positive 0.000042 moles per liter second. The negative sign represents that NO2 is a reactant and that it is being consumed during the reaction, and the rate of disappearance of NO2 is being given. Let us do one more question. Calculate the rate of appearance of nitric oxide for the second 100-second interval. Pause the video here and try to answer this question. For the second 100-second interval, the initial time is 100 seconds and the final time is 200 seconds. And the concentration of NO at 100 seconds is 0.0035 molar. Since NO is a reactant, its concentration increased to 0.0052 molar at 200 seconds. Therefore, the rate of appearance of NO, that is delta concentration NO divided by delta T, is equals to nitric oxide concentration at 200 seconds, which is 0.0052 molar, minus nitric oxide concentration at 100 seconds, that is 0.0035 molar, divided by 200 minus 100 seconds. If we do the math, we get 0.000017 moles per liter second. As you can see, the rate is already a positive number. Therefore, we can say that the nitric oxide is the product in the reaction and that we are calculating the rate of its appearance. One of the disadvantages of average reaction rate is that whenever we talk about it, we need to specify the time increment in which it is calculated. That is, if it is a 50-second interval or a 100-second interval or something else. So, instead of average rate, we can use instantaneous rate to express how fast the reaction proceeds. In the next slide, we will learn what an instantaneous rate is. Instantaneous rate is the value of the reaction rate at a particular time point. If we take the average reaction rate and pick the smallest possible time interval, that is, the delta t approaches 0, the reaction rate we get is called as instantaneous reaction rate. The instantaneous rate is represented by d concentration divided by dt. If average reaction rate is analogous to average velocity of the car, then instantaneous rate is analogous to the velocity of the car at any moment in time. That is, the odometer reading on your car at a particular time. The instantaneous rate at a particular time can be obtained by computing the slope of the tangent to the curve at that time point. The instantaneous rate at time t is equals to 0 is called as the initial rate of the reaction. And the initial rate of the reaction is the fastest. And over time, the instantaneous rate, that is the slope of the tangent to the curve at various time points, decreases. Later in this chapter, we will learn why the rate decreases over time. Earlier, we learned two different ways to express the reaction rate. That is, the rate of appearance of products or the rate of disappearance of reactants. The rate of appearance of products and the rate of disappearance of reactants are indeed connected to each other. For example, let us consider the following reaction. 2 moles of NO2 gas gives 2 moles of NO plus 1 mole of O2 gas. According to the stoichiometry, for each 2 moles of NO2 consumed, we get 2 moles of NO and 1 mole of O2. So, at any particular moment in time, we can say that the rate of disappearance of NO2 should be the same as the rate of appearance of NO. That is, at any instant of time, if 50 molecules of NO2 are consumed, then 50 molecules of NO must be formed. Mathematically, we can represent this by the following equation. Minus d concentration NO2 divided by dt is equal to plus d concentration NO divided by dt. Let us now look at the relation between NO2 and O2. According to the stoichiometry, for every 2 moles of NO2 consumed, we get only 1 mole of O2. So, at any moment in time, we can say that the rate of disappearance of NO2 is twice as fast as the rate of appearance of NO. That is, at any instant in time, if 50 molecules of NO2 are consumed, then only 25 molecules of NO are formed. Mathematically, we can write this as the following equation. Minus d concentration NO2 divided by dt is equal to 2 times d concentration O2 over dt. If we combine both the equations, we get minus d concentration NO2 over dt is equal to d concentration NO over dt is equal to 2 times the d concentration O2 over dt. Let us divide the entire equation with 2. We get minus 1 over 2 d concentration NO2 over dt is equal to 1 over 2 d concentration NO over dt is equal to 1 over 1 d concentration O2 over dt, where 2 is the stoichiometric coefficient of NO2 and NO, and 1 is the stoichiometric coefficient of O2. So, for any hypothetical chemical reaction, A moles of A plus B moles of B gives C moles of C and D moles of D. The rates of formations of reactants and products are connected to each other by the following equation. The overall rate of the reaction is equal to minus 1 over A dA over dt equals to minus 1 over B dB over dt equals 1 over C dC over dt equals 1 over D dd over dt. We can express the same relation for average reaction rates as well. Let us now do an example problem. Consider the following data for a hypothetical reaction. We have concentrations of A, B, and C at various time points. What is the reaction equation? That is, we need to find out the stoichiometry of the reaction equation. First, if we look at the data, we can say that the concentration of A and B is decreasing over time and concentration of C is increasing. Therefore, we can say that A and B are the reactants and C is the product of the reaction. Let us now find out the stoichiometric coefficients of A, B, and C. In the earlier slides, we learned that the reaction rates with respect to the reactants and products are related to each other by the following equation. The average reaction rate is equal to minus 1 over A delta A over delta T is equal to minus 1 over B delta concentration B over delta T is equal to 1 over C delta concentration C over delta T. As you can see, I put negative sign in front of A and B, which are the reactants. So, from the data, if we can calculate the rates of disappearances of A and B and the rate of appearance of C and arrange these things in the above form, we can calculate or determine the stoichiometric coefficients of A, B, and C from the above equation. For that, we need to determine the relative rates of appearance of products and disappearances of reactants. Let us pick a time interval and calculate the reaction rate in that time interval. I am going to pick the entire time interval, that is 4 seconds interval. Next, let us calculate the rate of disappearance of A, that is minus delta A over delta T, which is equal to concentration of A at 4 seconds, that is 0.75169 molar, minus concentration of A at 0 seconds, 1 molar, divided by 4 seconds minus 0 seconds. If we do the math, we get 0.06 moles per liter second. Similarly, let us calculate the rate of disappearance of B, which is minus delta B divided by delta T. That is concentration of B at 4 seconds, which is 0.50338, minus concentration of B at 0 seconds, that is 1 molar, divided by 4 seconds minus 0 seconds. If we do the math, we get 0.124 moles per liter second. Next, let us calculate the rate of formation or appearance of C, that is delta concentration C over delta T. This is equal to the concentration of C at 4 seconds, 0.49662, minus concentration of C at 0 seconds, that is 0 molar, divided by 4 minus 0 seconds. If we do the math, we get 0.124155 moles per liter second. From these three equations, we can write 2 times minus delta concentration A over delta T is equals to minus delta concentration B over delta T is equal to delta concentration C over delta T. Or if I divide the entire equation with 2, I get minus 1 over 1 delta A over delta T is equal to minus 1 over 2 delta B over delta T is equal to 1 over 2 delta C over delta T. As you can see, we have negative sign in front of rate with respect to A and rate with respect to B. Therefore, these are reactants, as we've already mentioned, and C is the product. The stoichiometric coefficient of A is the denominator here, which is 1, and stoichiometric coefficient of B is 2, and stoichiometric coefficient of C is also 2. Therefore, the stoichiometric equation is A plus 2B gives 2C.